When you look at a clear solution in a test tube and wonder what's actually swimming around in there, well, in chemistry, that's a puzzle we have to solve all the time. Today, we're going to crack the code for identifying the most common negative ions, or anions, that you'll need to know. Think of us as chemical detectives. By the end of this, you'll have a complete toolkit to unmask these invisible ions. Let's get right into it. So imagine this. You're in the lab, maybe it's a practical exam, and someone hands you a test tube. It looks just like water, but you know it's full of different ions. So the big question is, how in the world do you figure out what's in there? That's the core challenge of qualitative analysis, and today, we are going to master the techniques to solve that exact problem. Okay, here's our game plan. We'll kick things off by learning how to spot halide ions. Then we're going to move on to ions that give themselves away by producing a very specific gas. After that, we'll nail down the test for sulphate ions. And to wrap it all up, we'll put together the ultimate revision guide, your master cheat sheet for all these tests. Right, first up on our list, the halides. We're talking chloride, bromide, and iodide ions. Identifying these guys involves a really clever multi-step process. It might look like a bit much at first, but you'll see there's a perfect logic to it, where each step builds on the last to give us a solid, definite answer. So before we do anything else, we have to ask a crucial question. Why add dilute nitric acid first? You might be tempted to just jump in with the main chemical, right? But hold on. This first step is super important. We add the nitric acid to get rid of any other ions that might be lurking around, like carbonates, which could mess up our results and gives a false positive. It's like clearing the board before you make your big move. It makes sure any clue we find is the real deal. So here's the 4-step plan in action. Step 1, acidify with nitric acid to remove any imposters. Step 2, add our key reagent, silver nitrate solution. This is what we hope will react to form a solid, what we call a precipitate. Step 3 is just observing that precipitate. That's our first big clue. And finally, step 4, we use ammonia solution to confirm our suspicions and be 100% sure of what we found. Okay, so you've added the silver nitrate. Now it's time to play detective and look for that precipitate. If you see a white solid form, that's a huge pointer towards chloride ions. If it's more of an off-white, kind of cream color, you should be thinking bromide. And if you get a really obvious, distinct yellow solid, well, that's screaming iodide. This observation gives us our prime suspect. Now pay close attention to this, because it's a massive exam tip. Telling the difference between a white and a cream precipitate can be tricky, right? Your eyes can play tricks on you. That's exactly why the next step, using ammonia to confirm, isn't just a nice to have. It is absolutely crucial for getting the right answer, especially under exam pressure. And this is how we nail the culprit down. Let's say you have that white precipitate. Add some dilute ammonia, and if it dissolves, bam, you've confirmed it's chloride. Now for the cream one. Add dilute ammonia, and nothing happens. It stays insoluble. But then you add concentrated ammonia, and poof, it dissolves. That confirms you've got bromide. And that yellow iodide precipitate, it's just stubborn. It won't dissolve in dilute or concentrated ammonia. Case closed. So what's actually happening chemically in that test tube? It's really simple. The positive silver ions from the silver nitrate are finding the negative halide ions in your solution, and they're instantly sticking together to form those solid precipitates that we see. You absolutely have to know these ionic equations. They come up all the time. All right, toolkit's out. Let's add a couple more tools. The next tests rely on a totally different kind of clue, gas. We're going to be on the lookout for a very specific smell or some telltale fizzing. This is how we hunt for ammonium and carbonate ions. Okay, let's put these two tests head to head because it's a great way to remember them. For ammonium, we use a base, sodium hydroxide, and a little warmth to produce a pungent, smelly gas. For carbonate, we use an acid to get an odorless gas. See? The reagents are different, the gases are different, and the way we confirm them is different. It makes them super easy to tell apart. Let's walk through the ammonium test step by step. First, add your sodium hydroxide. Then you warm the mixture, and notice it says gently. We are not trying to boil it. We just want to gently encourage the gas to come out. Then you hold a piece of damp red litmus paper right at the mouth of the test tube to test the gas as it escapes. And that's the money shot. The second that damp red litmus paper turns blue, you've got your answer. That's the definitive proof that the gas is ammonia, which means your original solution had to contain ammonium ions. It's as simple as that. So what's the chemistry here? Well, the hydroxide ions that we added from the sodium hydroxide basically pull a hydrogen ion off the ammonium ions that were already in the solution. This reaction forms the ammonia gas we detected, along with a bit of water. Now on to carbonates. This test is often way more dramatic. As soon as you add some dilute acid, you're looking for fizzing, or to use the proper term, effervescence. That fizzing is your first huge clue. It tells you a gas is being produced, and now our job is to figure out what that gas is. To do that, we need to bubble it through some limewater. And this right here is the classic, absolutely foolproof test for carbon dioxide. The moment that perfectly clear limewater solution turns milky or cloudy, you've confirmed it. The gas is CO2. And if the gas is CO2, it means your original unknown solution must have had carbonate ions in it. This ionic equation shows you exactly where that fizz came from. The carbonate ions in your solution react with the hydrogen ions from the acid you added. This reaction breaks the carbonate down, forming water and, of course, the carbon dioxide gas that we saw bubble up. Okay, time to add the last major tool to our chemical detectives toolkit. This test is for finding sulphate ions. And just like the halide test, it relies on forming a precipitate. It's a really reliable one. Now, this procedure might look a little familiar. Just like we did with the halides, we start by adding acid, hydrochloric acid this time, to get rid of those pesky carbonate ions that could interfere. Then we add our key reagent, barium chloride solution, and we just watch and see what happens.
And if you've got sulphate ions, you'll see a thick, dense, white precipitate of barium sulphate instantly form. But here's the absolute clincher. That white precipitate is totally insoluble in the acid we just added. It won't dissolve, it won't disappear. And that's how you know for sure that you're looking at a sulphate.
And the chemistry is, again, a simple pairing. The barium ions that we added find any sulfate ions floating around in the solution, and they lock together to form that solid, insoluble barium sulfate that we see as the white precipitate.
Phew! We have covered a lot of ground, building our toolkit one test at a time. So now, let's bring it all together with the master key, a single summary that puts every single clue, reagent, and result in one place. And here it is. This is the whole story on one slide. Your master key. It has every ion, every reagent, every observation, and every confirmatory test we've talked about. This is probably the most important screen to have for your revision. So seriously, pause here, take a screenshot, burn this into your brain. It connects all the dots.